let's start. So what I was actually planning to, so now, I think we made a lot of progress the last 2 lectures and can relax slightly. And so what I was planning to do now for a few minutes maybe, but maybe you have more questions and maybe this takes longer. If it takes longer, no problem. Before I start the lecture, I was just going to pull up some example ODE code, which you can actually download. They already downloaded from the webpage, right? Is it true? Soon. Anyway, now is the lecture. So before the exercises, you will be able to download that, and you can just compare the ODE code which you have done with some other implementation. I think it's very useful to just see different implementations. This one is in Python. Actually, I do have one in Fortran 90 as well. I'm not sure. This one I think is maybe a bit cleaner, a bit simpler, and maybe we just go through it and just briefly, and you can look at it afterwards. Just compare with your implementations. Okay, so actually you're going to see 2 files afterwards on this webpage. There's going to be one. Can you actually read this? Okay, is it all right? Yeah, all right. So there's going to be 2 files. This maybe is hard to read. The one is called ODE_base. That's like the basic implementation of the Runge-Kutta functions and also some plotting functions, just the basic infrastructure. And then there's a second file which is called ODE examples, which is a very short one, just to implement different ordinary differential equations, which all use the same basic infrastructure to do Runge-Kutta. So, for example, if you want to do some different problems, it's kind of nice to have your code organized maybe in this way. The basic core algorithms that allow you to solve some general problem of, in this case, ODE type. They're in some file, in some package, and then you have another one which implements the actual physical problem that you're interested in. All right. And so most of this code actually was written by Michael Purr. 99% of it was written by Michael, who is a postdoc in Cardiff, and at most 1%. Maybe by me. I just split this into 2 files and organize a little bit more and clean it up a bit. So this is Python. So Python usually starts with importing all kinds of packages. I think several of you are using it, right? So there are plotting libraries, and then there are libraries that, for example, give us some of the that enhance the linear algebra tools. And actually, let me start with the base package first. But you see this starts just in the same way. If you use if you use Octave or MATLAB, maybe you also have to import some extra package you want to use, or use C. You maybe use some library. So whatever code you have, you may well have such a kind of a header where you import different libraries. Then here, part of this general infrastructure is already some example. Here I define some function. It's called ODE right-hand side example of u and t. So this is the part which, for some ODE, defines y prime equals f of t and y. Right, so this function here, so it's an example function, and u is a vector here. So this routine is able to deal with systems of ODEs, and just to help me understand what the variables meant in this function, I actually give names to the components of u. Here I just call this a simple example. I just call them x and y, and then I have x right hand side, in this case it's minus x, y right hand side minus y, just to have a simple example. Okay, and then it returns an array which consists of x right hand side and y right hand side. So far so simple. What's here to point out? I try to put variable names which mean something. Okay, ODE right hand side example, x right hand side, y right hand side. Okay, I didn't just call things u and u1 here inside and u1, u2, because if you look at it after 3 weeks, you don't remember what they were. If you give it some name that means something, it's easier. Here, inside this little function, I call things, x and y, but maybe because here locally you may understand what things are, but if you have a little bit longer names that explain more, This is always useful, right? Okay, so far so good. And then we need some functions which define the different integration methods. So I think this is what most of you have done. You have defined one function which just takes one time step of the Runge-Kutta method. So here I have three functions. One is called Euler step, one is called RK2 step, one is called RK4 step, which doesn't fit here. And these two, I think you remember we had them actually on the slides on the first day. I just made a copy of this code, right? So you have seen this already. So very simple. I think all of you understood what's going on here. Just a straightforward implementation of the Runge-Kutta methods, which we discussed in the lecture. But I made them separate functions here just to make things simple. I just have to modularize more. They all look the same. They're all written in the same style, which also helps us to make, if once you have understood the Euler step, which is kind of very simple and obvious, then you can see that the other ones are just a slight generalization, so it's very easy to understand what is going on. The arguments of any of these functions, so it's of course it's u and t, the time step, and then also the right-hand side function. So what you see that here, while it carries out one of these Runge-Kutta steps, of course it has to call the right-hand side function. It has to call this function f, and I'm actually passing this function as an argument, so that the same Euler method, the Runge-Kutta method, works for any right-hand side function. I don't have to, and this is something which, when you write some numerical code to solve some problem, ODE or whatever it is, it's always useful to just write it in such a way that it solves a bit of a general class. Not too general that makes it a lot of work, but just general enough. You don't want to write a separate code for every single ODE that comes across your path. You can write one ODE solver for the Runge-Kutta method and write it in such a way that it just can take any right-hand side function. Right? And this also is done in such a way that the first thing it asks is, what's in the length of the vector u, so the number of components of that system. So this function can deal with any number of components in this ODE system. Okay, so here we have defined our Runge-Kutta methods, our three methods, and then what else do I have to do? Well, I have to have some kind of loop which loops over all the time steps, right? So that's the next thing, and I implement that as a function. Okay, it's not the highest level of the program. The highest level of the program is still reserved for more general tasks. And here's just a loop that goes over the different time steps where I want to evolve. I call this here, I put a comment, this is the ODE integration driver. So the thing that drives execution of the Runge-Kutta time steppers for a single time step. What are the arguments? So this is U0, well, the initial data, the time step delta t. I have here ODE stepper. What is that? Also ODE stepper is again a function which I can, there's a parameter, and it could be Euler step or Runge-Kutta 2 step or Runge-Kutta 4 step, right? So this function doesn't really care whether I'm going to integrate this with Euler or with some other method. And if I'm going to implement yet another method, right, it also doesn't matter. It's just completely opaque. It doesn't care. All right. And then I included another, of course, ODE right-hand side, like before. It's just that whatever function that defines the right-hand side of this ODE. I also leave that free. And then I pass some parameters, which here is just a list. It's an array for all the other parameters which I might communicate to the execution, which here I needed 3. T max, well, the maximum time I want to evolve to, something which is called n steps max, the maximum number of steps I want to allow, and n equations, the number of equations. Okay, I'm just extremely bad with picking names. Okay, I've worked with somebody who worked for a while in computing in industry, and he was a genius at picking names that really mean something. Not too long, but still, to tell you what it is, and they're kind of consistent. I'm terrible at this, but I try to do not do a terrible job. Okay, so it's something that is quite important. It's worth thinking about. what should you call these things? Okay, that it means something.
What does it mean? Zeros and then something in bracket.
0 and then something in bracket. Where is it?
Zeros.
It's here. Okay, so this is the first element. Okay, right. So this is always something to be careful about. So this is a very good point, right? If you have an array, a list, right? Some programming languages like Fortran, they say that the index of the first element is index number 1. So if you want a first element, you have to say sol of 1.
I think she asked me what the zeros function in number.
Sorry. Here, this thing here.
Zeros function. NumPy zeros.
Sorry. So this is some library. Okay, this is some library function which comes from this package in P. Let's just go up what it means, right? Let's just check. So I said somewhere, where is it? Import numpy as MP. It's numpy is some package. What it's gonna do? My mic is. Is it better? All right. All right. Well, what's from the name? What is numpy going to do? Well, pi apparently stands for Python, and num for numerics. So it seems to be some library which defines some numerical functions that are useful. Okay. And here what it does, so this is where we have imported that, and in Python we have the freedom to import this library, but then give it a local name, which is just shorter, which is quite common that people do. Not so sure if it's a good idea, but less typing. Right, and so now let's go back to, now we have seen where it comes from, and now let's try to understand what it does. So it just says, npy is np.zeros, even without going into the Python syntax. Okay, what it means apparently is this is a function which is called zeros, which is associated with this np library. Okay, and it just creates a vector of size n steps in an equation, a matrix. Okay, and it creates a matrix where the entries are all zeros. Why is it doing that? To allocate the memory where we store afterwards the solution. Okay. So if we were to do that in C, we would have some array, and first you have to allocate the memory, or in Fortran you declare an array of these dimensions, for example, and here we just use this linear algebra function to fill a matrix with 0. So now we have allocated the memory. Okay, and here we set our initial data. So we're lazy. We just always say, okay, t is equal to 0 initially. Don't have any more freedom to have a different value here. U is U0. We start with iteration n equals to 0. So this is Python numbers. The first element is number 0. Right, so you really have to be careful. It may easily happen that you switch between different languages. One of them starts numbers things by 1, 1, 2, 3. One other one by 0, 1, 2. And if you switch between different ones, I don't know, you write C, but then you plot your things or analyze things with another language, it's very easy to make mistakes, or just miscount elements by one item, right? And then we have a loop. Go over all the time steps until we think we're done. So it's here, it's done as a while loop. And what is the condition? While n is smaller or equal than the number of steps, here a number of steps minus 1, and t is smaller than the maximum value, go to the loop, go inside the loop, and update your solution u by calling ODE-STIFR, which is either Euler, Runge-Kutta 2, Runge-Kutta 4. Once you have updated, increment the counter of n, define solution step n as this new solution u, and increment the time step, and at the end return the solution. Simple, right? Maybe a few comments are in order. So first of all, so here we have two conditions. It has a specified number of time steps and a specific number of times. So if either of these conditions becomes satisfied, it just stops. And that's quite useful. Right? You may say, I want to go up to t equals 10, but if it turns out this requires too many time steps, let's just stop before. But you could also add some other conditions. For example, yesterday with some of you we discussed, but we we integrated this equation for r dot, which described the in-spiral of these two particles. But if r is smaller than 2m or m, this doesn't really make much sense anymore. So we could have just added another, for this purpose, another condition here, that as soon as r is smaller than some threshold, stop. Right? Okay, and then another thing that's worth mentioning here is what we're doing here is we fill up this vector sol with the solution values at each time step, right? So sol is actually a matrix, right? It's a n steps by n equations matrix, because now we have a system. So if it's three differential equations for n steps, then we have a 3 by n matrix which holds the solution. And we compute the whole solution in this one step. Afterwards, when we do partial differential equations, we may not want or be able to afford that, because here we load the whole solution for all times into memory. But if you have a partial differential equation, we have more dimensions in x, which makes this solution much larger, right? Let's say if you have 100 grid points in x, this thing would be 100 times larger. If you have 3 dimensions, 100 times 100 times 100 larger. Well, we may not have that much memory. So quite typically, if you do PDEs, we compute one time step, we save the solution, and we don't keep it all in memory, just too much. Okay? But here, if you can keep it all in memory, it's convenient, and we will do that here. But for PDEs, this is probably not necessarily a great idea. I mean, one dimension is still, modern computers have a lot of memory, but probably makes sense to just save things once in a while. Okay, so then in principle we are done. We have just 2 more routines which we also defined as separate functions. One is called ODE save and one is called ODE plot. And so obvious what they do. So this function just takes the solution, just saves it into a file, and the other one just plots it. Because in Python, like in many other of the tools that you use, you can just, while you're computing it, you can also do some plots. So this is maybe nice to just control what's going on. But also, it's really, really useful. Plotting things right away is very nice, but then you close the window and it's gone. So probably a good idea to just also save all the data files, because then once you've saved them, you can also look at these data files with other tools, maybe the GNU plot or whatever you want to use, right? Okay. So, well, code to save a file is not extremely interesting or mathematically fascinating. Let's just have a simple, just a look of what we're doing here. So the first argument here is a name. So that's a good idea, because we have the freedom to change the name of the files, right? Because depending on what problem you want to solve, maybe you want to keep this freedom of changing the name, or you produce solutions at different resolutions, and you could call them, H1, H2, H3, or something like that, right? And choosing a good name, not just for the functions, but for the data files you produce, is maybe even more important, because if you look at the function, if you look at it, if you look at the variables, you can figure out, maybe it's a little bit more difficult if you have chosen bad names, but you can figure out what it does. If you have written this data file, which has really interesting results, and you want to look at it 2 years afterwards, it's helpful if the name tells you something what the hell is going on, right? In practice, it's not quite working like this. You always wish you had stored more information, made things more clear. Happens to me all the time, but just let's try. All right, so you can look at this by yourself in more detail. Let's point out here. So there's another convenient function in this NP package, which is called save text. What is it doing? Apparently, so it defines some name and then just saves. Well, actually, we don't see all the code here. Scrolls. There's some formatting strings here, and it just saves this array to a file. And apparently this language is quite elegant, because what we're doing here with these plus signs, we just add different strings together. to make a bigger string. So we had this kind of name, which could be, for example, we pass like H1, H2, H3. Then there is this another array which is called sol names, so solution names. Why we put that? Because maybe in our program we want to define, we have this vector ODE solver, but then the names of these components, they mean something to us. Maybe the first one is the pressure, and the second one is the mass, or whatever it is. And when we save these objects to a file, it would be nice to not call them, H1 Y1 dot that, but H1 mass dot that, H2 mass dot that. It just helps us to keep track of what's going on. And then I don't want to talk too much about the plotting thing. It's just there's this standard plotting package which you can load in Python, which is this matplotlib, and it has reasonably easy to follow here. What's going on? Plot, subplot, it just plots different subplots for different things. Show, actually put it to the screen, puts labels, puts a title, and so on. All right. And then, so you have defined a bunch of functions. And now we need some kind of main routine. There's this kind of nifty feature in Python that you can start your main routine with this funny piece of code here. If name equals main, do something. And so what we have, since this is a bit tricky, we took the luxury of putting a comment here. And so now we can import this file as a module without running main or execute it as a script. So we have this kind of library thing defined here, which defines several functions. But depending on how we call it, we can just import it as a library or directly execute. Okay. Now let's not look at this because I wrote a separate file. So here we wrote this to just be able to directly execute and test the file which defines all these functions to integrate ODEs. But then I did a separate one which is just the problem-specific one, which is much shorter, and is the one to modify if you want to solve different problems. Right? It's always kind of convenient if you have, the basic infrastructure is in some files, in some directory maybe, and then the code which the user who wants to solve different problems, the user has to modify and just keep it separate. And so we start in the same way, importing all kinds of libraries. Here now, we say, from ODE base, this was this other package which we wrote, import all the functions. And then here we define the ODE thing which we want to solve. Here we call it my ODE right hand side. Lack of more inspiration of finding a name. And this is here the only function which we define. Okay, because all the rest we have done in this base package. And now we have this driver. So here we specify all our variables, number of equations, Tmax, maximum number of steps. We form this array which contains Tmax, n steps, maps, and equations. Set the initial data, set the time step, and then I just call ODE stepper 3 times. Sorry for the 3 different resolutions. So I set dt1 to dt0 to this value, set the step size, call the ODE integrator, say, when it's finished, some message, stop that, this number of time steps, this state, this is the final state vector, the final solution, and I call ODE save and ODE plot. And then I just do this for half the time step and a quarter the time step because I don't want to do the convergence test, right? And then, to make my life easy, I also compute these differences, which we looked at for the convergence test. So I call them here, I call them diff1, 2, which is solution 1 minus solution 2, and diff2, 3, which is solution 2 minus solution 3. So, right, so here, solution 1 was the coarse, solution 2 with the final grade, and solution 3 with the best grade. Right? And what else have I done here? What is this strange thing with these colons here? There is this, as in many of the languages that they're using, there's some kind of array syntax implemented. So what this here means is take this array Sol 2, go from, so the general, it's worth specifying this because even in Fortran or Mathematica or MATLAB you have always very, very similar kind of syntax. So we could go from your step n to step m in steps of S. So this says start at element m, n, go to element m in steps of S. If you leave this out, it just says go from the first to the last in steps of S, right? That's what it's doing here. So go over all the elements in steps of 2, and here go over all the elements in steps of 4. Because the final solution has 4 times as many steps, so we only save every 4th one, right? And I will just compute these differences and save them, and then we can plot them afterwards with nuplot if you want. So let's just check whether I screw this up, and let's check if it's actually running. You never know. So let's execute that. Where was it? So Python ODE examples. Let's make it slightly larger maybe. You can actually read that. Here we are. And so now it's running, and it says stopped at the first entry. And so remember, so this was what was my system? It was y prime equals minus y. Basically, I had basically 2 copies of this solution. And remember that my time step here was just this limit. So my dt0, my initial time step was this number 2.78784 or whatever it was that we discussed the other time, the maximum time step. And or just below, and so certainly this doesn't look quite like an exponentially decaying function, or it's at least decaying, it's not blowing up, okay, but it doesn't look like anything like the solution. Well, let's click this away here. Now it executes the second one, so this is half the time step, and now it looks like the proper solution, okay, it looks reasonable. We can see if you don't see it very well maybe, but if you look closely, you can see that here it's quite not very well resolved, right? This curve is not a nice smooth curve. It more or less looks like, okay, so we're now at half the maximum time step. It looks, something like the real solution, but we have to make h much smaller to get it accurate and nice. Let's click this away. Let's execute the third one. And so now this looks much, much better. The curve looks reasonably smooth. We have evolved it now for a time scale which is much longer than the one on which it decays. And no late time effects that it's, sometimes you could have a numerical instability where initially things look okay and then suddenly it becomes unstable and explodes. That doesn't seem to happen. So it seems to be all right. And so now we could, what I'm not going to do here because you have all done it, now we could do the convergence test and really plot the differences and see whether, so now the curve looks smooth and nice. Now we have a chance that this convergence test passes and we're roughly in the regime where the simple formula of the leading order behavior is accurate and when we pass our convergence test. All right, and so now you can download this. Well, the Python gives us all kinds of, has many things to say, which we can ignore. And you can have a look at it also, just to compare with how you have solved the problem, how maybe you get some ideas of how to simplify things, give things better name, and so on. It is worth, once you have done something, to just clean it up a little bit, ask yourself how you can make it nicer. And so now let's proceed to the next part and what we want to learn today.
This course are now on today.
Ah, great, thanks, excellent. So what we want to learn today, and if you don't learn it today, well, we will learn it today, right? How to turn our ODE solver into a solver for PDEs. Okay, so let's proceed. And so what we do today is we look at finite difference schemes for partial differential equations. And what we're going to do later in the lab, we will code up the wave equation, our first PDE, and just to make life simple, we're going to use periodic boundary conditions. Okay? And then tomorrow we'll try maybe to start with non-periodic boundary conditions to have some more interesting physics. And the other thing which I think would be good for you to try is just to derive, I will later in the lecture I will derive the second order centered finite difference stencil with one method, and you can try it with another one, which is just using Taylor expansions. Okay. Now, so first let's just go through what we learned yesterday. Yesterday we learned some basic theory of hyperbolic partial differential equations, which we have a nice initial value problem. There were all kinds of things that were a bit more abstract. So now that we have learned these things, let's look at some simple examples again before we go into the finite differencing. So the wave equation in one space dimension. So here it's a scalar equation, and now just to have things a bit more interesting, I put back the c. So this is the propagation speed. So here's where our equation. Now we can, from this second order equation, we can obtain different forms if we want. So one thing that we could do is we could obtain a so-called mixed first and second order form. We introduce a new variable, which is pi, and we define it by phi comma t is pi. Actually, it's convenient to multiply that with c. Okay? And then from this definition and the wave equation, we can compute what is pi dot, pi comma t is phi comma xx. Okay? Why would we do this? Well, because afterwards, we have already seen that it's convenient for ODEs to convert everything to first order in time, whatever the order of the equation is, and so to put it in a standard form. So let's just do this, and you will also later see in Thomas's lecture that it's quite standard and convenient to put the Einstein equations into this form that you have first order in time and then maybe second order derivatives in space. Right? You've seen already that the Einstein equations, they are second order in time, second order in space, but it's quite standard to time derivatives to convert them into first order. Right? Okay, we can also do more. We could also reduce it completely to first order and replace all introduce even more variables. Here we have introduced the variable psi, which just is phi comma x, and with psi we can now write down the evolution equations for for pi and for psi, and you see now, of course, we expect that because psi encodes the space derivative, the first space derivative, that now the new evolution equations for pi and for psi, they just contain first derivatives of x. Okay? And remember that yesterday when we talked about well-posedness, we talked about first order hyperbolic systems, and now we have cast the wave equation into this form, into a first order hyperbolic system. All right? So there are these different ways of writing the wave equation. They can be convenient for different purposes. All of the three have their, sometimes it's more useful to solve this form, and sometimes we want to do something else. Okay. There is in the third way, there's a subtlety which is important to understand. This definition here, psi is phi comma x, means we have introduced a constraint in our system. Because if now we evolve phi and pi and psi, now we can find, because there's numerical error, that during the evolution, if you evaluate phi comma x numerically, it's not going to be the same as psi anymore, because there's some error. Okay? So this takes, if the true solution, for the true solution is satisfied, but for the numerical not. Okay? And we are not free to choose the initial data for psi as we want, but at the initial time, of course, we have to choose them in the form that we just take them as the derivative of phi. We cannot choose whatever data we want from psi. Right? We have to choose phi, and from that we compute the derivative, and now we know psi. All right. You remember we discussed this thing for the Maxwell equations. There were also constraints, and they're preserved by the evolution equations. And of course, we have the same thing here. You can just take the time derivative of the constraint, use your evolution equations, and you find that the time derivative is 0. But of course, if you do it numerically, you have to worry a little bit but it is also true on a discrete level. All right. There's another funny thing which is going on here. We see in this form that in order to compute pi dot and psi dot, we don't actually have to know phi. Okay, so we should actually just solve for these two variables, pi and psi, and if we want to know phi afterwards, we could then afterwards, after we know pi, just integrate up phi comma t equals c pi, and then we know phi as well. Okay, this is it's a special funny feature that when we convert it to this form, the phi has actually dropped out. Obviously, if you wouldn't have the wave equation in this form, but you would have some term some lower order term which involves phi, like the Klein-Gordon equation, like we would have plus m squared phi, or some potential of phi, then it couldn't drop out. Right? And in one of these equations we still have m squared phi. Right? Okay, but if we don't have this, then the evolution equation for the scalar field itself decouples, and we can just look at the equations of psi and pi. Now, let's write them down. Yesterday we worked with things in this matrix form. Let's just do this in this case here, when we discussed first order systems in this matrix form. So we have something like dtu is a dxu, and u is a vector and a is a matrix. U is the vector which has two components now, pi and psi. And then we can compare this form with these two equations and figure out what are the matrix components. You can play around with that, and you will see that the matrix is 0, 0, C, and C. Okay? In particular, it's not in a diagonal form. Okay? So, if you follow the description that we did yesterday, we want to find out what are the eigenvalues, what are the eigenvectors, and what would be the diagonal form of the equations. Well, this is a simple 2 by 2 matrix, so it's easy to compute these objects, and so we find that A has eigenvalues plus minus C, and the eigenvectors are minus 1, 1, and 1, 1. Okay? Now, what does that mean? Yesterday we learned that we constructed these characteristic variables. I'm not sure what I called them yesterday. I think did I call them W? Not sure. So these are, right, they had the four, we wrote this down yesterday in the slides. This would be the similarity transformation P times the solution vector. P was the matrix of the similarity transformation. We had something like D is equal to P, A, P to the minus 1 inverse, right? So it's this matrix which diagonalizes the matrix A. And then if you apply this basis transformation to the solution vector, it's a linear combination of the components of U such that now our equation becomes diagonal, right? So the new equation would be omega 1 dot equals lambda 1 dx omega 1, so W1, and W2 dot equals lambda 1 lambda 2 dx W2, right? Or in other words, the vector omega, it's W1, W2 dot is equal to the matrix W1, W2 is just propagated with a speed, here with a speed lambda 1 and here with a speed lambda 2. Okay? So the equations for the characteristic variables are very simple. It's just that these fields are just propagating at a particular speed. Let's write them down explicitly. So we have said the eigenvectors are minus 1, 1 and 1, 1. This means that these characteristic variables, they're called here W. Here I call it U plus minus, because here one is psi plus pi, this one here, and the other one is the negative difference. The other one is psi minus pi. Of course, if psi minus pi is a characteristic variable, minus that is also a characteristic variable, right? Pi minus psi is the same, because its eigenvectors are only defined up to multiplication with a number, so you can do psi plus pi, psi minus pi, or pi minus psi, is as you like. And then these variables, they satisfy these advection equations. So the time derivative of u plus or u minus is plus or minus c dx of u plus minus. Okay? All right. Another thing that we have seen yesterday is that the solutions, they will preserve the norm. And so since they prefer the norm, they are well posed, and we've seen that yesterday. In particular, we see that one of the ways to see that the norm is preserved is that since each of these is an advection equation, the norm of that is just but then we have some initial profile, and just the profile moves in time, and of course since it's the same profile, it has the same norm, right? So it's well posed. Okay, so this was one example. Let's look at a different example. Yesterday we had these definitions of weakly hyperbolic, strongly hyperbolic. Let's look at one which was weakly hyperbolic. So I claimed that these are in some sense bad. So let's look at them. Let's look at one of them. So consider the following simple system in one space dimension. U dot is equal to, so we have now two components, I call them u and v. U dot is dx of u plus v, and v dot is dx of v. Looks like a nice, harmless, simple partial differential equation, right? Nothing looks wrong with it. Now let's write down the whole system as a matrix equation, so we can look at these coefficients, and we find out that now the matrix is 1, 1, 0, 1. Okay? And we don't actually have to diagonalize. We already see that this doesn't work because it has exactly this Jordan normal form that we talked about, with diagonal here, but it has this one off diagonal element. So that's not going to work. Okay? It's not diagonalizable. If we do the standard eigenvalue analysis, we see that there's only one proper eigenvector, which is 1, 0, with eigenvalue 1, and then there's a trivial one, a trivial eigenvector with eigenvalue 0. So it's not diagonalizable, it has no complete set of eigenvectors, it's only weakly hyperbolic. Okay, but weakly hyperbolic is some name, some definition that we made. What does it mean in practice? Let's look at some solutions. This is a simple system of equations. We can write down some explicit solution. Here we choose a solution with frequency omega. Okay, so let's write this down. Our solution is u is equal to omega t, a sinus function, and v is sinus omega times t plus x here. Which also looks quite reasonable at first sight, but actually we see that there's a problem, because the sinus is okay, but there's a linear growth in t, and it's also proportional to the frequency omega. Okay, so it shows some frequency dependent growth. If you compute the norm, right, we do this norm of the solution at time t divided by norm of the solution at time 0. We see that it grows asymptotically linearly in t. Now, linear growth in t is completely fine. Exponential growth in t would also be fine. But it also depends depending on the frequency of the initial data. So for example, if I show you some initial profile, okay, let's say this is my initial profile, okay? Of course, we could Fourier transform that, and this has all kinds of different frequencies in it, okay? And so here, the highest frequencies, they would grow faster, and this doesn't seem to be a viable physical solution, because the more high frequencies I have, for example, the more frequencies I can resolve in a numerical scheme, the stronger it would grow. This is very strange. And so this is a simple example. What happens if for a bad equation, for one which is not well posed? Let's just look at very, very quickly at another example. And so this is the York ADM equations. These are the ADM equations, the ones that Thomas is going to derive for you. Okay. And so these equations are very nice because they have a very simple geometric interpretation. Is that this is the basic geometric interpretation which makes us understand in which way we're going through the space-time, time step by time step. Let's just apply this nice hyperbolicity partial differential equations analysis to these equations. Let's make our life simple. let's consider plane wave traveling in the x direction. Questions? Thomas is going to explain to you also this thing with gauge conditions, which we have to choose. For the moment, just let me say that there's something which we have to choose. We have chosen it here. Let's forget about it again. Then we make life even simpler. We linearize these equations around flat space. Because it's a plane wave traveling in the x direction, everything just depends on x. And we can write down what these equations are. Okay? And we see there are 3 equations. We only have x derivatives here because everything only depends on x. And we can now, we have converted everything to first order in time. We have introduced the extrinsic curvature. Right, so look at this equation. It's like h dot, h is the metric dot equals 2k. It's very, very similar to what we have done just before for the wave equation. For the wave equation, we said, this was phi was our basic evolution variable. Phi dot equals pi. So pi is analogous to this variable k, the extrinsic curvature. And it's not a surprise that they have this very similar form because the principal part of the Einstein equation is also like a wave equation. Okay, so this is not surprising at all. So we have written this down. Now we can do the work. We compute this matrix A, and this is what we get. And we see again, it's not diagonal. There are these 2 Jordan blocks here, one and here the other one. So quite annoyingly, these very nice and very elegant and simple equations do not give rise directly to a well-posed initial value problem. Okay? So which means that if you want to solve the Einstein equations numerically, we will have to do some massaging of these equations. Okay? And we can do this in many ways. And so this is one of the stories of numerical relativity, is actually how to massage these things. And one of the ways to do something which works is this BSSN system, which Thomas will also discuss for you. Now, so now after 1 hour. Well, let's just take, we're not at a half, but let's just take 2 minutes break anyway, just to refresh ourselves before we continue. Now I'll tell them to you tomorrow because we have to move on a little bit so that we can do the exercises afterwards. But doesn't matter. Equation, so that we can put it on a computer. And let's do this first in a very, very simple way, but it works. So here we have a simple grid. This is a space-time grid right here. This is the space direction. That's the time direction. It's an equispaced grid. Here's our equation now. We forget about the c again. Set it to 1. UTT is uxx. And we take a grid where x goes between 0 and 1. We start at t equals 0 and then evolve for positive t. We set some initial data. U of x and 0 is u0. Time derivative of u at initial time, we call it v0. And to keep things simple, we do periodic boundary conditions first. If you do periodic boundary conditions, that means right, all points are equal. Right? There's no point which is like the boundary of the grid. We can, when we evolve, we choose a boundary, but we identify this point with this point. So really all points are physically equal. Right? Okay, you have to think of one of the things that let you think about when you implement the wave equation is how do you actually in your code, how do you implement this periodic boundary condition that u of x equals 0 is u of x equal 1 for all times. Okay, you have to make this identification going around the loop. How do you do that? Well, then we have an equispaced grid in time and in space. We'll just write this down. And then we do the following straightforward algorithm, which is called also the leapfrog algorithm, which is the discretized time and space in the straightforward way to second order accuracy. For example, for time, we just say that the second time derivative at time step n and grid point j is equal to this combination of values of grid points with coefficients. So it's uj, and so we want to compute the utt at grid point n and spatial grid point j, and then we take the difference of uj n plus 1, this one plus this one minus twice the value in the middle, right? So this is the error that we make here is order of delta t squared. So this is second order accurate. And obviously, if you can do this, utt second derivative in time direction is discretized in this way. We can do the same thing in the x direction, right? And we just write the same thing in the x direction, and then we rearrange the terms, and we say uj n plus 1. So this value can now be expressed from this one and this one and this one and this one, right? And so we just rearrange our terms, and we get that uj n plus 1 is twice uj n, so twice this one, minus this one, plus a combination of these three, and we just to make things shorter, we call this here the coefficient lambda squared, and lambda is nothing but a shorthand of delta t by delta x, because they don't have to be the same, right? Okay? So this is just, it's a simple algorithm that we can just come up with, straightforward. And now what do we expect for that? Well, we saw that, so this is a way to just integrate things up step by step. We have seen for ordinary differential equations that not necessarily we can make a time step as large as we want. So maybe this will only work if delta t is not too large. We have to check that. Okay, so let's just look at that.
Where does this requirement come from? Is it easy to see that?
Yeah, I'll talk about it in two different. So it comes from two different angles, and we'll talk about it. Okay. So the first, so one is a more geometric one, and one is just a question of stability in the sense that we have looked at it before, but the solution blows up or is damped out. Let's so it's a linear equation. A linear equation, we can write it as a superposition of Fourier modes, all right? And so we can write it as a superposition of this kind of Fourier mode, like e to the I omega some frequency, j the grid point delta x. Right? This is like j delta x is x, right? Because we have this equispaced grid. There's nothing as e to the I omega x. Okay, if you want, you can call omega k, like the wave vector or lambda. Usually for this kind of analysis in numerical analysis, is more typical just call this thing the spatial frequency, to call it omega. Okay, and so then what's going to happen is that the solution, when we insert this discretization algorithm, right? When we go from time step n to time step n plus 1, it's just apply some operator, which essentially corresponds to multiplication, to our Fourier mode. Okay, and then it turns out this is just some number q to the n. And so at every time step, we pick up some multiplicative factor. Okay. We can also check that the way that we have set up the grid, with this wave number of frequency omega, we can see that omega delta x has to be smaller than pi. We'll look at this a little bit more afterwards as well.
uj is each mode, isn't it?
Use the solution at time step n, say. No. Okay, it's just an expression. This is an expression for the solution, and we can evaluate it at time step n and at grid point j. Okay. So we can call this q. We can call this an amplification factor, and if this amplification factor is larger than 1, then the algorithm is going to be unstable because this amplitude is not going to go to infinity. Okay. The time dependence of the solution is that we look at it now in a discrete way. So at the time step n, and so the time step is this frequency, this like a eigenfrequency, multiplied with q to the n. Right? This is not a general solution. general solutions, they look more complicated, the time update. But this is one which just has, it's just a plain wave with a particular frequency. Okay, and for this one we can check that it has this very simple behavior. For general, not. For general solution, not. Okay, it's just for this plain wave, because of course the general solution we can write it as a superposition of plane waves with all kinds of frequencies. And for if you want that the solution remains stable, each frequency has to remain stable. So we can just look at a particular frequency and just check what happens during the time evolution. That's what we do. That's the logic. Okay.
Here you are looking at the plane wave solution.
Right. Exactly.
Just for understanding, is there should be a factor of with t means omega x is there.
Sorry, say again.
In general, the plane wave, so you take the factor of kx minus omega t in the exponential. Means I'm not understanding that thing.
So this is, we write the solution as like, spatial waves, like Fourier transform in x, the same way that we have written it down yesterday in the continuum, just Fourier transform in x. I mean, it just takes such a basic wave in x, insert it into our iterative scheme and check what happens. And we find it's just, that's what happens with just this simple expression. Sorry? No, why is it based? This is just a value. You tell me which grid point you want, and I tell you what number comes out. We don't have to sum over it. No, it's just a function of you tell me a time step, and you tell me a spatial step, and I tell you what's the result, what's the solution. Okay.
Sir, if q greater than 1, is that particular mode is unstable or a whole solution is unstable?
Well, we have to do this calculation somehow, mode by mode. And so the solution is going to be stable if all the modes are stable. We will see this in a second, right? That some modes may be stable, other modes may be unstable. And the solution, of course, is only stable if all the modes are stable. Another thing is that we have to think about, to just interpret what's going on here. If you have a smooth solution, okay, then the signal has to be concentrated at small frequencies. The appropriate variable that we could say as small, we call psi. This is like omega delta x. This is the thing which is where we can check that. You can check it for yourself. That this is always the way we've set it up. Our grid. This is always this is pi, right? Pi. So this is a dimensionless variable, okay, which is however we discretize it, if we normalize things like this, then this frequency goes from 0 to pi. And if it's a smooth solution, then we cannot have contributions which have very, very high frequencies. Okay? If our signal is well resolved, then we can't have high frequencies. We'll return to this afterwards. I'll show you a few more pictures. Okay. Now, just to do the calculation, we can insert our ansatz into the discretization, evaluate this, and then here we have some here lambda squared. So we'll get a quadratic equation in lambda, which was delta t over delta x, for the condition that the norm is equal to 1, which is like the boundary. And we can solve this quadratic equation and check what's the maximum lambda which is allowed to satisfy the condition that the amplification factor is not allowed to be smaller, so it's not allowed to be larger than 1. Okay? And so in this condition we just get a maximum time step. Okay? What we can also do, instead of just solving this equation, we can also just plot things. This is not, you don't see this very well here, but what is this? This is here on this axis we're plotting this variable psi, the frequency of the wave, plotted from 0 to pi. And on this axis we have plotted lambda, delta t over delta x, from 0 to 1 point something here. It starts with 0 in the back, because put 0 in the back because at small lambda nothing's going to happen. And we're just plotting this amplification factor, we're plotting this Q. Okay? And so what we see is that it's 1 for for small lambdas, everything's okay. But then suddenly, for some lambda which is a bit larger than 1, at the high frequencies, at frequency higher than some value, and you see the first one where it goes bad is here at the highest frequency pi. There are two solutions. The amplification factor rises larger than 1. So that means that if you just at this limiting value, which would here be behind, at lambda equals to 1, actually, lambda equals 1, and the frequency equals pi, you violate the condition and the amplification starts to become larger than 1. If you make your lambda equal larger, if you make a time step even larger, then the instability goes to lower and lower frequencies, and this will also become unstable. Okay, but at this lambda, whatever this would be here, my plot ends at lambda equals 1.1 maybe or something like this. Of course, things are already very bad. As soon as one frequency is unstable, as soon as for one frequency the condition is violated, it doesn't work anymore. Okay, that's how this works. This is for the advection equation, but you can see this for the advection equation. We get a very similar picture, but things start to break down not at the highest frequency, but just in the middle, for the middle frequencies.
So phi is the field that you want?
No, sorry. If you can read this, forget what's the axis here. It's this frequency psi here. The normalized. The normalized grid frequency. And the thing we do this because independently of how many grid points we use, this quantity is always normalized that it's up to pi. Okay, and so whatever grid we use, we'll get the same plot. That's everything, right? All right.
Can you make so omega is determined by the function that you are sort of solving for. That's the spatial frequency.
Omega is the spatial frequency which you have put in your initial data, right? And it's essentially the fundamental frequencies which are possible to represent in that grid. Okay?
And
if you have a
grid space that you're
right. I'll show some more pictures now afterwards, but here's just the basic.
I'm sort of trying to get a sense into this correctly. So the Qn is like a Fourier amplitude of this sort of
right.
isn't it?
Right.
So,
right.
This could be just a physical. Like you can have a physical solution that has a growing Fourier amplitude. Isn't it? So why can't in general you can, but in this case here, because it's a linear equation without source terms, you cannot. Okay. Of course, that's why. So there's another thing you have to point out. So we do this test we test the algorithm in the case where there are no source terms and there shouldn't be any growth. In a more complicated equation, there can be different reasons of growth. There can be because it's just growing, and because the algorithm is unstable. It's the same. It's exactly the same logic that we have applied for the ordinary differential equation. Okay. So just to repeat that, right? So what we have said that let's take the wave equation. Let's just make a straightforward grid, a straightforward discretization, which we can derive by ourselves. Let's think about we can somehow write the solution as a superposition of Fourier modes. Then we just analyze each mode separately. For each mode we get a condition whether it's stable. For each mode we get a condition on the maximum time step. And if this condition is violated for any of the modes which we have in the grid, it doesn't work. That's our prediction. You will test it afterwards in your codes whether that's really true. So this was one way of seeing that the time step cannot be too large because we create this growth. But there's another one, a geometric one, and that I want to explain now. In general, this is called the Courant-Friedrich-Levy condition, or just Courant condition, which sloppily we mean some condition which restricts our time step. Let's look at this in a geometric way. Let's consider some scheme which has some explicit time stepping. So here, this is our initial grid points, and we go to these, we go to these. Okay. Now, there can be two things, and to understand what's going on, I have to remind you of this definition we made yesterday, the domain of dependence, right? Let's forget about grid points for the moment. Let's look at the continuum domain of dependence. This is what I've drawn here and here, right? This is like the backward light cone, okay? Now, we can, so this is a continuum domain of dependence. What's the discrete domain of dependence? Well, it's the thing with the points, right? So if for our finite difference scheme, that these points determine these points and this point, so this point is not determined from all of those. And here the same. But now there are two different cases. We can have the case where the numerical domain of dependence is bigger, or the physical domain of dependence is bigger. And we have to think about what that means. What's the interpretation of that? Okay? And now, so this is written here. We can think about this when we'll see that the numerical domain of dependence should include the physical domain of dependence. This is this case. The numerical domain of dependence is larger.
So means the numerical domain of dependence is like the sum of points they use to compute.
Right, exactly. Right, exactly. Because if this is not true, in the other case, here, the physical domain of dependence is larger. Okay? So what does it mean? That this grid point here, physically, in the continuum, it can be influenced from this region here, but numerically it can't, because numerically it's only influenced from this one. This one is out of reach. Okay? So what this means is that we simply cannot converge to the correct solution because we're just neglecting some relevant physical information. Okay? We cannot reproduce the correct physical solution because we just have thrown away this information. Maybe this information changes this value, but we just kick it out. This is not logically consistent. Okay? How do we transform this solution into this one? We just have to use a smaller time step. Okay? Just deform things with a smaller time step, and then we go to this case. Okay? So one is like c, this is the propagation speed. So c is, tells us what's the inclination of this angle here of the speed of light, of the passed light cone, and we have to compare the path c times delta t with our grid spacing. If it's smaller, we are in this case and it's stable, and if it's larger, we're in this case and it's unstable. If we're in this case, simple solution, just make delta t smaller. Okay? Well, this is a necessary condition because if it doesn't happen, it's just not consistent. It's certainly not a sufficient condition. The sufficient condition is the one which, in this case here, which is derived, doing the stability analysis, doing this linearized stability analysis, and see whether solutions are exploding or not. Okay? But usually you will get similar or very similar or exactly the same answer, at least in one dimension, just from the geometric argument. Something that is worth mentioning is if you have parabolic, you could wonder if you have parabolic equations, which in relativity are not important, in other fields yes, but we said that parabolic equations have like instantaneous propagation of information. So does this mean that you cannot use an explicit scheme at all because it's just, that the maximum time step is 0? Well, it is not quite true. It just turns out that the restriction is not that delta t has to be smaller than delta x, but just goes with delta x squared, which is much, much more restrictive. Okay? And so in this case, because it's so restrictive, you will have to use methods which circumvent this problem, and these are implicit methods which we really don't want to talk about more. But if you do, chemical reactions or heat transport or so, then this is a completely different topic. You have this condition and you use different methods. Okay, so now that we have warmed up to this thing of grids and so on a little bit, let's look at this again, the whole picture with the frequencies. Let's just write it down in detail. So consider some equispaced grid. Let's just do it general in d dimensions. Then the d-dimensional grid is, of course, it's just the tensor product of the one-dimensional grids. The one-dimensional grids, remember, xj is just, so for writing as j times h, and then j goes in our numbering just from 0 to n minus 1. So we have n grid points. We can, if you want, just to jump to these plots here, right? If you have a grid of n points, you can represent on this grid different frequencies. Yeah? And so, for example, here I had 160 grid points, and I choose a frequency such that you have 32 points per wavelength. And if you evaluate this variable psi, then you will see that this amounts to pi over 16. Yeah? You use half the resolution, double the frequency. So you have 160 grid points, 16 points per wavelength. It's twice the frequency, so it's not pi over 16, it's pi over 8. Okay, and then here, 8 points per wavelength. You know, certainly this one and even this one, they're not well resolved anymore. Okay, if I want to expect that I can find an accurate numerical solution, I have to have like a smooth function with many points per oscillation. Here I certainly don't have that. We can.
Use something like an IISc theorem?
It's the same. Yeah, it's the same. Yeah. But since here, what we want to do is we want to have an accurate representation with a finite difference method, which means we're just taking a few points. We have to have things nicely resolved, like in this picture. If the frequency becomes too large, well, we just have to use more grid points, right? Which means that in this normalization, this value psi is just going to always to smaller values, far away from pi. Okay, let's just write down some of the details. So we will call vectors on this grid, we will call that grid functions. For such grid functions, we have an inner product, which is just, the kind of the standard scalar product, but we have to multiply this with the power of the grid spacing so that we get consistent numbers for different grid spacings. We could, from the scalar product, we could derive a norm. And then we have already seen yesterday the stability criterion for the discrete case. So we have to say that there exists constants k and alpha, so that the solution at time step n is bounded by the solution at time step 0. All right? This is just taking the condition of continuity from the continuum level to the discrete level. And so now we can ask which frequencies we can represent on this grid, which frequencies omega we can present on that grid, and we find this, we go from minus n over 2 plus 1 plus 2 and so on to n over 2. So this frequency is omega, right? That the more grid points we have, the higher frequencies we can represent. If you want to, for practical purposes, it's useful to just rescale the omega with the grid spacing, introduce a new variable which we call psi, because after the rescaling, the grid just goes from minus pi to plus pi. And then we always have the same grid, which just makes things easier. That was the thing that we saw before, which just plotted things here, which just plotted things in this rescaled variable from 0 to pi. In fact, of course, we have positive frequencies and negative frequencies. So just here to save space, I just plotted the positive ones.
Why are we calling it linear stability analysis?
Sorry?
Why are we calling this linear stability analysis?
Because we're doing it for a linear equation. So, since we're working here with Fourier, a Fourier decomposition, it's really based on linearity. The basic idea here, this was the same yesterday for the continuum problem. The basic idea is that we're using Fourier analysis, and we can't do that if it's not a linear problem. Okay? If it would be a nonlinear problem, we have to consider a linear perturbation of a nonlinear problem, and then a detailed mathematical analysis shows that essentially things carry over. Just have to consider, a linear perturbation. So the fundamental analysis here is really for the linear problem. All right, so now we have laid out our grids. We have two ways of writing the frequency in a rescaled way, and in this way where we go up to frequencies of n over 2, and then we can say, you know, a grid function v at time step n is just superposition of these different Fourier modes. These create Fourier transforms. Let's call it the Fourier modes v hat n, for example. And these are the coefficients which depend on the frequency times this Fourier frequencies e to the ix, e to the I omega xj. Okay? And then the Nyquist theorem tells us what's the highest frequency which we can represent on the grid, which is exactly the one that we wrote down here. Okay. Now this was just some layout of setting up our grid and making the statement that we always want to be able to jump between real space and Fourier space. Okay. Now the next thing is let's derive some finite difference stencils. Yesterday we have on Monday already we derived the first order finite difference for the Euler method. I just told you Runge-Kutta 2 is this formula. Now let's derive the second order stencil, which I just used here for the wave equation. This one, let's derive that. Okay? So we can derive it in different ways. So one is to just use Taylor expansions, and I suggest you do this by yourself. Or here another simple way, which is of course equivalent, we use approximating polynomials. What does it mean? For example, let's derive this second order centered, we'll see what that means, finite difference stencil. So we want second order accuracy. This means that we may approximate the solution by a second order polynomial. Okay? So we say that that's our model for the solution. That has three coefficients. In order to find these three coefficients AI, we need like 3 grid points to define their values. We have to sample the solution at 3 grid points to determine these 3 coefficients. So let's have a grid of 3 grid points. To keep things simple, I call my grid minus h, 0, and h. And we want to have a centered formula, which means that we want to evaluate the expression for the derivative at grid point 0 using values at all the 3 grid points. All right. So having that set up, we get equations. This function at position minus h is going to be some value, which is just call that f1, and so forth for the other 2. Okay? And now we can solve this for our coefficients, and we see that the coefficient a0 is just the value of the function at the second grid point, and the coefficient a1 is this formula, and the coefficient a2 is this formula. Right? In this case, for example, it's quite obvious that a1, the Taylor series, a1 is just the derivative of x, the derivative of the function f. So that's going to be the answer for how to compute the derivative from the values of the functions. And this is for the second derivative up to a factor of 2, right? But now we can just do this explicitly, in which we say now, so this was our model. We have computed our values of the coefficients. Now we can take the derivative of this function, first derivative or second derivative, okay? And then just computing the derivative of this function would now be f3 minus f1 divided by 2 times the grid spacing. So that's our approximation for the first derivative up to second order in h.
How do you get A2?
Sorry?
To see how to get this particular form of A2?
The particular form of A2.
Yeah.
Why you get that? You mean like an intuitive argument when it has to be that?
Yeah.
Well, I think you can intuitively. So first of all, it's wrong because I mistyped it here, and here it's correct. Okay. First of all, intuitively, what is clear intuitively? Intuitively, it's clear that there's some kind of parity. So the first derivative, there has to be like odd parity between this grid point and this grid point. But for the second derivative, there has to be like even parity. So obviously, so for the first derivative, they have a different sign, and for the second derivative, they have the same sign. Okay, this one obviously has to be with inversely proportional to the first power of h, and this one to the second power. I would say, for the particular coefficient 2, I think having some intuition about a kind of a symmetric parabola, probably you can have intuition about this one. But of course, for general higher order, I don't think that intuition is going to go very far. You have just to do the same calculation. You want fourth order stencil, take 4 more coefficient, do the same procedure. You get, what are you going to get? What is it going to look like for fourth order? Well, you need 2 more coefficients, which means that 2 more grid points to determine the answer. If you want it centered, you need one grid point more here, 1 grid point more there. So second order, we need 3 points. Fourth order, we need 5 points. Sixth order, 2 more. Right?
So I'm also confused about the general procedure. So you know that A2 should be the second derivative of f.
Mm-hmm.
So how would you get this from that?
How do I get?
A2 from that. So the A2 would be like partial square f by partial x.
Well, so we can see that we can see it actually here now. We can see it 2 ways, right? I mean, this is a Taylor expansion, right? So we can see that A2 is just f double prime divided by 2, and so once we have solved these equations for the a's in terms of the f's, we already know that wow, that's going to be the formula for the second derivative. Or we say I don't see that. Just take now f, take 2 derivatives. I had 2 derivatives at, I made one little mistake, right? That nobody told me that. We have to say we want a derivative now at point 0 in the central one. So we have to insert these expressions and then set x equal to 0. And then we get this expression, for example, for the second derivative. And just now this tells us second derivative at x equals 0 is this expression. So if I want to know what's the value of the second derivative, take 1 times the value to the right plus 1 time the value to the left minus 2 times the value in the middle and divide by h squared. That's your approximation. And if you want it fourth order, then it's going to be 2 values more with different coefficients. Okay? But this is the one that's the one that's easy to derive by hand. Okay? Let me just I'm going to do this with the Fourier space afterwards, because now I just want to do this slide and then we can stop, because this is what you need to get started, and that's the method of lines. 2 minutes, the method of lines. What we have done before for the wave equation, just having this space-time grid, that's a so-called direct space-time discretization. We have done one formula, in some sense, to directly write down, to have a space-time stencil and directly write down a formula of how to update the next time value from some previous values. Okay. Now, in this case, it's very difficult to generalize this to higher order, okay, and to analyze the stability. You would have, for every case, you have to do this. And there's this very nice trick to circumvent all these problems, which is just to discretize space and time separately. Okay. And what do? We have some equation. Oops, there's another typo here. It's like dxu, right? We have some equation. Let's say the advection equation. Okay. And then we just keep time continuous, and we just discretize in space. Time, we don't touch time. So if we do this here, we discretize in space, then dx of u just becomes, with the formula which we just derived, u at the grid point I plus 1 minus u at the grid point I minus 1 divided by 2 delta x. What is this? It's a system of ordinary differential equations, right? For each grid point, we have an ordinary differential equation. So n grid points, n ODEs, and they're all coupled because this ODE is coupled to the value, one to the left and the one to the right. So using this method, we have suddenly converted a partial differential equation to a set of coupled ODEs. And you have already written a code to solve coupled ODEs, so you're done. Okay? You just have to couple you have to use this ODE, couple the different ODEs in this way, and here you have your partial differential equation solver. It's all done. Okay? A separate kind of point of view on this is, and then now you have your ODEs, right? And then just this thing now that it's split, you just solve this with your Runge-Kutta method, which you have already done. Why may this not work? Why to do this stability analysis and so on? We saw that this doesn't always work. But in the limit, delta x goes to 0 is the limit of infinitely many coupled ODEs. It's a singular limit. And just as we discussed for ODEs, you have to take this limit of having infinitely many time steps. You may not be able to really carry out that limit. It may not really work. That may give you trouble. And that's why you may find that such PDE discretizations are not stable. And it could turn out that, for example, this works fine, but if you would have discretized in a different way, it's not okay, and it's just that there's an obstruction really carrying out that limit. Okay? So, no, well, it's not a constant, it's just in our sense, it's a parameter. It's like the parameter of the ordinary differential equations. And again, as for your ODE solve, I start at t equals 0, and then I solve these coupled ODEs until I have t equals t max, right?
Suppose there are three variables, t, x, and y. Then take t as a parameter.
Right. You mean you have two space dimensions, right? So then two space dimensions. If it's first derivatives in two space dimensions, you just do the same formula in the x direction and the y direction. If it's second derivatives, then you have to think about, there could be like dxy derivatives. What do you have to do with those? You think a little bit about it. But in principle, you just proceed in the same way.
This procedure actually decreases the partial order of the differentiation by 1. Because suppose x, y, and t, you keep x and t as a parameter.
Mm-hmm.
And
you mean that if you have two space dimensions, you could somehow always also convert it to ODEs in the other one. Yeah, you could do some. Yeah, you could do that, but it turns out the standard thing to do is you convert it to ODEs in the time dimension, and then the rest you just discretize, and you treat all the other space dimensions the same. Okay. How to integrate the ODEs? Well, any stable ODE integrator, the same that we discussed yesterday. If it's an explicit integration, there will be time step conditions which depend on the ODE integrator that you use. If it's implicit, this will be much relaxed, so there are no conditions. And this is very, very nice just to write scientific code. It's very easy to now, you plug in, interchange things in a modular way. You have the same time integrator, but you change the space integrator. You have the same space integrator, just change the Runge-Kutta method here. Just try different things. That's very easy to try, easy to maintain the code, easy to be flexibility. And somehow flexibility, robustness, simplicity, which you have in this scheme, these are very, very important to really solve scientific problems in a reliable way. So these are high virtues. And then, just to finish today, you can derive the following theorem, which is we formulate this in a sloppy way here. If you have a first order constant coefficient hyperbolic system, okay, like the wave equation, for example, then the discretization will be stable if you use a centered finite differencing stencil, which is derived it for second order, and some simple time step restriction. We'll talk about what is the restriction of the time step, but for the moment, you can code up for the wave equation, this thing here. If you want to warm up to the wave equation, you do the advection equation first. Right? We have seen that in some sense the wave equation is just two advection equations anyway. You code it up in this way. And then just check what time step you can use. And if the time step, you have seen for ODEs what happens if the time step is too large, check what happens for PDEs if it's too large. Okay? Wave equation falls into the scheme, so you're all set up. All right? We'll look at that in the afternoon.